Two machines launched in 1977 are now farther from Earth than anything humanity has ever sent into the cosmos. 13 billion miles into the void, Voyager 1 and Voyager 2 crossed a boundary that scientists once expected to be quiet, unremarkable, perhaps even invisible to their instruments. Instead, they found something that nobody had anticipated. Something moving. Something vast. Something pushing back against the entire reach of our solar system with a force that humbled every model and overturned every assumption that had guided space science for decades. A wall of plasma denser than any prediction had suggested. Particles racing at speeds that seemed to defy the physics of the region. A magnetic environment tangled and writhing in ways that theoretical models had never described. And a sound, a hum recorded in the data, translated into frequencies human ears could process, a sound that, by every reasonable expectation, should not have existed in the vacuum between the stars. What Voyager detected at the edge of our solar system is not simply a scientific curiosity. It is a revelation about the nature of the space we live in, the invisible shield that surrounds our entire planetary family, and the raw, turbulent cosmos that lies just beyond the reach of our sun's influence. The story of what those two spacecraft found begins not at the edge of everything, but right here, with two machines bolted together in a California laboratory nearly half a century ago, aimed at a darkness that no human eye had ever properly seen. The mission planners who conceived Voyager gave it what seemed, at the time, a beautifully simple assignment: fly past Jupiter, photograph Saturn, then drift away into the dark and go quiet. Nobody in the program seriously believed the spacecraft would last 5 years. A decade was unthinkable. 45 years of continuous operation, transmitting data, receiving commands, functioning in an environment of absolute cold and relentless radiation was the kind of outcome that scientists did not dare put into their official projections. The instruments were designed to survive a demanding journey, certainly, but longevity on this scale belonged to the realm of fantasy, not engineering specification. And yet both spacecraft were built with a durability that surprised everyone, including the people who built them. Voyager carried with it a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. Greetings in 55 languages, music from dozens of cultures, the sound of rain falling, of wind blowing through trees, of human laughter and ocean surf. Images of mountains, of cities, of human faces in every expression the photographers could capture. A message encoded not for any specific recipient, but for whatever intelligence might someday intercept a drifting machine crossing the dark between stars. A gesture of hope hurled into infinity. But the golden record was always something of a philosophical exercise. What mattered for science was the instrument package, the magnetometers, the plasma wave detectors, the cosmic ray detectors, the cameras and spectrometers and particle counters that would turn raw physical reality into numbers, and numbers into knowledge. What mattered was the data. And the data, it turned out, would keep arriving for decades longer than anyone had promised. Both Voyager spacecraft launched in 1977, and the timing was not accidental. The engineers and scientists who designed the mission had identified a rare geometric alignment among the outer planets that happens only once every 175 years. In this configuration, Jupiter, Saturn, Uranus, and Neptune were positioned in a sweeping arc that allowed a single spacecraft, properly aimed, to visit all 4 worlds using the gravity of each planet as a slingshot to accelerate toward the next. Without this alignment, reaching Neptune with existing propulsion technology would have required fuel quantities that no rocket of the era could have lifted. With the alignment, the planets themselves did most of the work. Jupiter's enormous gravity grabbed Voyager 1 and flung it forward with a velocity boost that no engine could have provided at reasonable cost. Saturn's gravity redirected that momentum upward, out of the flat orbital plane where the planets circle the Sun, sending Voyager 1 on a trajectory that would carry it above the solar system entirely. Voyager 2 took a different path, one that kept it closer to the orbital plane long enough to pass by Uranus and then Neptune, the most distant planet in our solar family. The two spacecraft became separated by billions of miles and traveled in different directions through the outer regions of solar influence, effectively giving scientists 2 separate measurement platforms. two independent probes of a vast and unknown frontier. By the early years of the new millennium, both spacecraft had left every planet behind. The familiar landmarks of our solar system, the giant storms of Jupiter, the magnificent rings of Saturn, the pale blue dot of Uranus, the deep blue of Neptune had faded to invisibility. The spacecraft were entering a region that scientists had named the termination shock, a zone where the solar wind, that continuous stream of charged particles blown outward from the sun at roughly 1,000,000 miles per hour, begins to lose its battle against the pressure of interstellar space. Think of it as a river running into the sea. The current does not simply stop. It presses forward with everything it has, but the sea pushes back, and eventually the river loses momentum, slows, and becomes something other than itself. At the termination shock, the solar wind crosses from supersonic flow to subsonic flow. The universe places a speed limit on it that the sun's own energy cannot overcome. The first anomalous reading arrived from Voyager 1-inch 2004. Scientists had constructed careful models of what the termination shock region should look like. The solar wind was expected to weaken gradually, the way a strong current weakens as a river spreads out into a delta. Measured values should have declined in smooth, predictable curves that instruments could track and theories could describe. What the data showed instead was something far more unsettling. The wind speed did not decline smoothly. It fluctuated. It dropped sharply, then surged back, then dropped again. The pattern repeated over months in a rhythm that resembled breathing more than physics. Something out in the dark was not simply resisting the solar wind. It was pushing back in waves, in pulses, as though the boundary itself was alive and moving. Then the cosmic ray detectors began registering behavior that the existing models could not accommodate. Cosmic rays are among the most energetic particles in the universe. They originate from some of the most violent events the cosmos produces: supernovae, the explosive deaths of massive stars, collisions between galaxies, the ferocious environments near black holes where matter is accelerated to near light speed. These particles travel across the galaxy at velocities approaching the speed of light, carrying energies that dwarf anything produced by particle accelerators on Earth. They stream through space in every direction, and they were streaming toward Voyager as it pushed outward from the solar system. Inside the heliosphere, the bubble of solar wind that surrounds our entire planetary family, the sun's magnetic field and the outward pressure of the solar wind act together as a partial shield. The cosmic rays are not blocked entirely. Some penetrate to the inner solar system, and Earth's own magnetic field provides additional protection. But the overall flux of cosmic rays is measurably lower inside the heliosphere than it should be in interstellar space. As Voyager moved outward, scientists expected cosmic ray counts to rise steadily, reflecting the decreasing effectiveness of this solar shield. The increase was expected to be gradual and monotonic, climbing toward values that would indicate Voyager had crossed into genuine interstellar space. The instruments recorded nothing of the sort. Cosmic ray levels jumped upward in sudden surges. They held elevated values for weeks, then dropped back. Then they surged again, higher than before. The pattern made no physical sense under any existing model. It was as though an invisible wall was appearing and disappearing, blocking cosmic rays during some periods and releasing them during others. A barrier that breathed, a threshold that oscillated. Something at the edge of the solar system was neither a clean line nor a smooth gradient, but a dynamic, fluctuating frontier that behaved unlike any boundary in the theoretical literature. The engineers ran every diagnostic available to them. Instruments 40 years into a punishing space environment had every reason to malfunction. The radiation alone over that span of time should have degraded sensor performance substantially. Temperature cycling from near absolute zero to solar heating effects had stressed every component repeatedly. Cosmic ray bombardment had flipped individual memory bits and altered electronic behavior in subtle ways that required constant management from the ground. It was not unreasonable to suspect that strange readings might reflect aging hardware rather than genuine physical phenomena. But the diagnostic results came back the same way each time. The instruments were functioning within normal parameters. The readings were accurate. Mission scientists began constructing a revised picture of what the solar system's edge actually looked like. The earlier models had imagined a relatively simple geometry, an inside region dominated by solar wind, an outside region dominated by interstellar space, and a transition boundary between them. The Voyager data suggested something more complicated, more dynamic, more alive in the physical sense. The solar wind does not flow at constant strength. The sun goes through activity cycles, periods of intense output alternating with quieter phases, and this variation drives the boundary outward when the sun is active and pulls it inward when the sun quiets down. Voyager was traveling through a boundary that moved, a frontier that shifted by tens of millions of miles depending on the state of solar activity. But even this revised model did not account for all of the anomalies. The magnetic field readings were perhaps the most puzzling of all. As a spacecraft moves from the inner heliosphere outward toward interstellar space, the direction of the magnetic field should change. Inside the solar system, the field reflects the sun's own magnetic structure, organized by the sun's rotation into a pattern that resembles a spinning sprinkler. Outside the heliosphere, in true interstellar space, the magnetic field has a different orientation, reflecting the broader galactic magnetic structure that pervades the space between stars. When Voyager crossed the termination shock, scientists expected the field direction to begin shifting, rotating gradually away from the solar orientation toward the interstellar orientation. The instruments recorded almost no such shift. The field lines kept pointing in approximately the same direction they had been pointing inside the solar system. It was as though Voyager had walked through a doorway and found itself in a room that looked identical to the one it had left. The door existed, the threshold was real, but the room on the other side was mysteriously familiar. In 2009, something more dramatic happened. The solar wind around Voyager 1 did not merely weaken further, it stopped. Not gradually, not over a period of weeks, as scientists might have expected from a smooth transition model. Within a matter of days, the outward flow of solar particles dropped to zero. The spacecraft found itself floating in a zone where particles no longer moved outward away from the sun, but instead traveled sideways, parallel to the boundary. This was a region no model had predicted. Scientists gave it a name that captured something of its unusual character: the magnetic highway, a corridor in which particles from both the solar environment and interstellar space flowed together in the same direction along aligned magnetic field lines. Ions that originated at the sun and cosmic rays that had traveled billions of light years from distant supernova remnants were moving through the same channel, briefly sharing a common path before diverging into their respective domains. Every model of the heliosphere ever constructed had imagined a two-zone structure: solar wind on the inside, interstellar medium on the outside, boundary between them. Voyager had revealed a third zone, a buffer region, a mixing layer where two cosmic environments interpenetrated and competed and occasionally collaborated. The boundary of the solar system was not a line. It was not even a thick membrane. It was a country unto itself, with its own physics, its own particle populations, its own temperature regime, its own magnetic structure. Scientists had studied the heliosphere for decades from the inside, building models and running simulations, and they had missed this entirely. It took a 40-year-old spacecraft running on a nuclear battery smaller than a carry-on suitcase to reveal it. Temperature in interstellar and near-interstellar space is a concept that requires careful unpacking. On Earth, temperature is immediately physical. We feel heat and cold through our skin. We experience the difference between a summer afternoon and a winter night as something vivid and continuous. Temperature in this everyday sense depends on the density of molecules, how many there are per cubic inch of air, how fast they are moving, how often they strike our skin and transfer kinetic energy to it. In space, the molecular density drops to values so far below anything accessible on Earth that the familiar concept of temperature almost stops making sense. A region of space can have a plasma temperature of 1,000,000 degrees and still kill an unprotected human in seconds through the cold that results from having essentially no molecules to transfer heat. What space physicists measure when they record plasma temperature is the average kinetic energy of the particles in the plasma, expressed using the same mathematical framework as ordinary temperature, but describing a physical reality utterly unlike the one we live in. With that understanding, Voyager's temperature measurements become even more extraordinary. In the solar wind region of the heliosphere, plasma temperatures run to around 100,000 degrees by this definition. The solar wind particles are moving fast. The plasma is thin, extraordinarily thin by terrestrial standards, but the individual particles carry substantial kinetic energy. As Voyager moved deeper into the heliosheath, the region between the termination shock and the heliopause, scientists anticipated that temperatures would fall. The solar wind was slowing down as it pushed against the interstellar medium. Slower particles mean lower kinetic energy. Lower kinetic energy means lower temperature. The physics seemed inescapable. The instruments disagreed with the physics. Temperatures in the heliosheath were climbing. In some measurement periods, they reached 250,000 degrees, 2.5 times higher than in the solar wind region closer to the Sun. The jump was large enough that some team members initially refused to trust it. Instruments on a 40-year-old spacecraft operating in conditions of constant radiation bombardment and extreme temperature cycling were not perfectly reliable. The possibility that the sensors were malfunctioning, reading artificially high values due to accumulated damage, could not be dismissed without careful analysis. The team spent weeks cross-referencing the plasma detector data with readings from other instruments, looking for inconsistencies that would reveal calibration drift or sensor failure. They found none. The readings were consistent across multiple instruments. And then Voyager 2, traveling through a completely different region of space, billions of miles away, on a trajectory that carried it below the orbital plane rather than above it, returned data showing the same elevated temperatures at the boundary region. Two spacecraft with separate instrument packages, traveling in different directions through different portions of the heliosheath, both recorded anomalously high temperatures. The probability that both instrument packages had failed in exactly the same way simultaneously was negligible. The readings were real. The temperatures at the edge of the solar system were far higher than theory had predicted, and the explanation required physics that was both elegant and humbling. When the solar wind reaches the termination shock, it does not simply slow down. The encounter involves compression. Billions of solar wind particles streaming outward at 1,000,000 miles per hour run into the resistance of the interstellar medium and begin piling up. The density of the plasma increases sharply. Particles that have been traveling freely through open space suddenly find themselves in a crowd. And when particles that have been traveling at 1,000,000 miles per hour suddenly encounter resistance and decelerate, their kinetic energy does not disappear. It has to go somewhere. It converts to thermal energy to heat in exactly the same way that air in a bicycle pump heats up when you compress it, or the way a meteorite blazes white hot as it compresses the air ahead of it while falling through Earth's atmosphere. The boundary region becomes a zone of extreme compression, a place where the solar system's momentum is converted into heat on a scale that spans hundreds of millions of miles. But compression alone did not fully explain the temperature values Voyager recorded. There was another mechanism at work, one that involved the behavior of magnetic fields in a way that has no comfortable everyday analogy. Magnetic field lines, the invisible structures that govern the movement of charged particles through space, have a property that physicists call reconnection. This happens when two sets of field lines from different sources approach each other, tangle, and snap apart in a new configuration. The reorganization releases energy suddenly and dramatically. Think of it as similar to what happens when you stretch a thick rubber band past its limits, and it breaks. The stored elastic energy releases all at once, and the broken ends fly apart. When magnetic field lines from the Sun's magnetic structure meet field lines from the interstellar magnetic structure at the heliopause, they can connect and disconnect in exactly this way, releasing bursts of energy into the surrounding plasma. Each reconnection event heats the nearby plasma, accelerates nearby particles, and sends waves of disturbed electromagnetic structure propagating outward in both directions from the site of the event. At the edge of the solar system, this process does not happen once and stop. The two magnetic environments are in continuous contact along the entire surface of the heliopause, a boundary that spans the solar system in all directions. Reconnection events happen constantly at different locations along this boundary, triggered by variations in solar wind pressure, by turbulence in the interstellar medium, by the continuous interplay of two vast magnetic systems that have been pressing against each other for the entire 4.5 billion-year history of the solar system. Voyager's instruments caught individual bursts of this activity temperature spikes that rose over the course of hours, then settled, then rose again. Each spike corresponded to a reconnection event somewhere in the surrounding region. The spacecraft was floating in a permanent fireworks display of magnetic energy release, a display spread across such enormous distances that each individual flash was invisible, only the accumulated heat revealing the ongoing violence of the boundary. The temperature measurements also carried information about the nature of interstellar space itself. The local interstellar medium is not a uniform substance. It has structure on scales ranging from individual cloud threads to vast bubbles and cavities carved out by ancient cataclysms. The region of interstellar space through which our solar system currently moves, astronomers call it the local interstellar cloud, or sometimes, more poetically, the local fluff has a temperature of roughly 13,000 degrees by the plasma temperature definition. This is far cooler than the boundary zone Voyager was measuring, but still hot by any human standard. A reminder that interstellar space, while cold in the density sense, is energetically active in ways that are easy to overlook from our sheltered vantage point inside the heliosphere. The local fluff itself is embedded in a much larger structure called the local bubble, a cavity in the galactic disk measuring roughly 1,000 light-years across, blown out by a series of supernova explosions that occurred over the past few million years. The gas inside the local bubble is hotter and less dense than the typical interstellar medium, and the solar system has been moving through this region for much of its recent history. The boundary conditions Voyager encountered at the heliopause were thus the boundary between the sun's own bubble of influence and this larger, older, explosion-carved cavity in the galaxy's structure. Every measurement Voyager made at the boundary was a measurement of where these two structures met. Scientists studying the temperature data began to piece together a picture of the boundary's small-scale structure that was surprisingly rich. The heliopause is not smooth. It wrinkles. It ripples. Solar wind variations create pressure waves that propagate outward and deform the boundary locally, creating protrusions and indentations. Variations in the interstellar medium press inward from the other side, creating their own deformations. The result is a surface that has been described as resembling the skin of a sun-baked beach ball, recognizably round from a distance, but covered in local variations that would be substantial on human scales. Where the boundary wrinkles outward, solar plasma pushes into interstellar space. Where it wrinkles inward, interstellar material presses into the heliosphere. Mixing happens at these contact points, and the mixing generates heat, which drives more mixing, which generates more heat. Voyager was not simply crossing a boundary. It was passing through a system of interacting dynamics that operated on timescales from seconds to millions of years, and on spatial scales from individual particle interactions to structures spanning the entire solar system. The spacecraft's instruments captured a single trajectory through this system, a line drawn through a three-dimensional environment of staggering complexity. From that single line, scientists were working to reconstruct the nature of the whole. It was like trying to understand the entire Pacific Ocean from a single transect line drawn by a small boat. Possible, with enough analysis, but humbling in its limitations. The plasma measurements that Voyager's instruments returned during this phase of the mission required software corrections that the original engineers had never anticipated. The instruments had been designed for conditions expected inside the solar system, conditions that were already extreme by human standards, but were relatively predictable. The heliosheath conditions fell outside the original design envelope in several parameters simultaneously. Plasma density was lower than the instruments were calibrated for. Temperature was higher. The magnetic field had a different character. Scientists had to develop new analysis techniques, new calibration corrections, new ways of extracting physical meaning from data streams that had been designed for a different environment. This took years. Some results that appeared in scientific papers in the early 2010s were later revised when better analysis techniques became available. The picture of the heliosheath that scientists hold today is built on 3 decades of iterative refinement, each cycle incorporating new methods and new insights. What emerged from all of this work was a portrait of the solar system's edge that differs from every prior conception in almost every detail. The heliosphere is not a simple bubble. It is not symmetric. It is not smooth. It is not static. It is shaped roughly like a comet blunt on the side facing the direction of the sun's travel through the galaxy, elongated into a long tail on the opposite side. The blunt face is where the solar wind meets the interstellar headwind head-on, creating the strongest compression and the most intense boundary interactions. The tail extends hundreds of billions of miles in the direction the solar system has already traveled, a long wake of solar material gradually mixing with the interstellar medium. Voyager 1 crossed through the blunt face, the most dynamically active part of the boundary. Voyager 2 crossed at a different angle, sampling conditions on the flank of the heliosphere where the geometry was different and the interactions had a different character. The comparison between the two crossing points has been scientifically invaluable. The measurements are not identical. Voyager 1 encountered a slightly different magnetic field configuration than Voyager 2. The plasma conditions differed in ways that reflect the asymmetry of the heliosphere's shape. The particle populations had different compositions. These differences carry information about how the heliosphere varies across its surface, information that a single spacecraft could never have provided. The accidental geometry of the 1977 launch, driven by the planetary alignment rather than any intention to sample different parts of the boundary, turned out to produce exactly the kind of comparative dataset that would have been designed deliberately if anyone had known what to look for. And through all of this, the spacecraft kept transmitting. The signal grew weaker with every passing year, not because the transmitters were failing, but because the inverse square law is implacable. Double the distance, reduce the signal power to 1/4. From Earth, receiving Voyager's transmissions required the largest radio telescope dishes available. The massive structures of the Deep Space Network pointed with extreme precision at a known position in the sky. Listening for a signal carrying less power than a refrigerator light bulb, arriving after a 22-hour journey across interstellar distances. The signal was there, faint. 19 watts of radio power, reduced by the time it reached Earth to levels that required the most sensitive receivers humanity had ever built to detect. But it was there. The signal that reaches Earth from Voyager is not simply a carrier wave bearing scientific data. It is a testament to what engineering can accomplish when it is done with patience and precision, and a willingness to think across decades rather than quarterly reports. The Deep Space Network stations that receive Voyager's transmissions are themselves remarkable machines, enormous parabolic dishes, some spanning more than 200 feet across, built in the California desert, and in Spain, and in Australia, so that at least one station always has Voyager above its horizon. The dishes must be pointed with an accuracy of fractions of a degree at a target so far away that even light takes 22 hours to make the journey. The engineers who operate these stations are, in a quiet sense, performing one of the most technically demanding communication tasks in human history every single day, and most of the world has no idea they exist. The data rate Voyager transmits at this distance has dropped to 160 bits per second. To put that in perspective, a standard modern photograph taken on a smartphone carries roughly 3 million times that amount of information. A single second of high-definition video carries more data than Voyager can transmit in an entire day. The spacecraft is, by the standards of the connected world we have built, an almost incomprehensibly slow communicator. And yet those 160 bits per second carry irreplaceable information. Every number in that thin stream of data represents a physical measurement made in a place where no human instrument has ever been before. The poverty of the data rate makes each bit more valuable, not less. The instruments that are still operating on Voyager 1 include the magnetometer, which measures the strength and direction of the magnetic field, the plasma wave system, which detects oscillations in the plasma that reveal its density and temperature, and the cosmic ray subsystem, which counts high-energy particles and measures their energies. The cameras stopped working long ago. There was nothing nearby to photograph, and the power budget required for scientific instruments did not allow non-essential systems to continue running. The heaters that keep certain components from freezing have been selectively turned off as power has diminished. Each decision to shut down a system represents a careful calculation. What can the spacecraft live without? And what is still producing data that justifies the power cost to keep it running? The power comes from radioisotope thermoelectric generators, devices that convert the heat produced by the natural radioactive decay of plutonium-238 into electricity. The physics of radioactive decay is as reliable as any process in nature. Plutonium-238 decays with a half-life of 87.7 years, meaning that roughly every 88 years, the amount of plutonium in the generator drops by half and the power output falls accordingly. When Voyager launched in 1977, the generators produced about 470 watts. By the mid-2020s, that figure had dropped to roughly 70 watts, enough to power a few incandescent light bulbs, barely enough to run the remaining scientific instruments and maintain communication. The trend continues downward. Engineers at the Jet Propulsion Laboratory calculate that within the next few years, power levels will fall below the threshold required to operate any scientific instrument at all. After that, the transmitters themselves will eventually go dark. Before that happens, the data coming back from interstellar space has already rewritten the scientific understanding of what lies beyond the solar system in ways that will take decades to fully assimilate. Among the most striking findings is the plasma density measurement that allowed scientists to finally confirm, with absolute certainty, that Voyager 1 had crossed into interstellar space. The confirmation did not come from any single instrument reading, but from an event that the spacecraft detected passively. Without any deliberate measurement, a ripple in the plasma triggered by a solar storm that had occurred more than a year before the spacecraft detected its effects. In 2012, a powerful eruption on the Sun, a coronal mass ejection, a billion-ton cloud of magnetized plasma thrown outward from the solar surface, propagated outward through the solar system. As this shock wave traveled, it compressed and disturbed the plasma along its path, creating a disturbance that moved outward at millions of miles per hour. When this disturbance finally reached Voyager 1, more than a year after the eruption that caused it, it set the surrounding plasma oscillating at a specific frequency that depends on the plasma's density. Voyager's plasma wave instrument detected these oscillations, a kind of ringing in the plasma, like a struck bell's note revealing the bell's composition. By measuring the frequency of the oscillations, scientists could calculate the density of the plasma surrounding the spacecraft. The density they calculated was 40 times higher than what the solar wind would have produced at that distance. It matched the predicted density of the interstellar medium with remarkable precision. Voyager 1 had crossed into interstellar space. Not at the boundary scientists had been watching for years, not at the dramatic moment when cosmic ray levels surged or magnetic field direction shifted, but at a point that the data only revealed in retrospect, using an analysis technique that nobody had anticipated needing. The crossing occurred in August 2012. The confirmation came in 2013. The scientific paper announcing it appeared in the journal Science, and the response from the planetary science community was one of the most emotionally charged moments in modern space exploration, not because the finding was unexpected exactly, but because it was suddenly, undeniably real. A machine built by human hands, launched on human ambition, carrying a golden record of human voices and music and images, was moving through the space between the stars. For the first time in 4 billion years of Earth's history, something made on this planet existed outside the solar system. The interstellar medium that Voyager entered is not what popular imagination typically pictures when the phrase is used. Space between the stars sounds empty. The distances involved are so vast that any material present seems negligible. The nearest star to our Sun, Proxima Centauri, is 4¼ light-years away, about 25 trillion miles. The space between here and there seems like it should be pure nothing. But it is not nothing. It is a thin but measurable plasma of hydrogen and helium ions, laced with dust grains, permeated by magnetic fields, threaded with cosmic rays, and filled with the electromagnetic afterglow of every energetic event that has occurred in the galaxy over the past 13 billion years. The density of this medium is extraordinarily low by any terrestrial standard, roughly 1 atom per cubic centimeter in the region around our solar system, compared to the 27 billion trillion molecules per cubic centimeter in the air you are breathing right now. But 1 atom per cubic centimeter, spread across the trillions of miles between stars, adds up to a substantial physical environment that shapes how light travels, how cosmic rays propagate, how planetary systems form, and how the heliosphere is structured. Voyager's measurements of this environment have already revealed that the local interstellar medium has more structure, more variation, more internal activity than earlier models suggested. The temperature, the density, the magnetic field direction, the composition, all of these vary on scales that matter for understanding how the heliosphere behaves and how the solar system interacts with its galactic neighborhood. Some of this variation may reflect the influence of the local bubble, the ancient supernova-carved cavity mentioned earlier. Some may reflect active processes happening now in the galactic disk. Some may be the signature of events that occurred millions of years ago, whose effects are still propagating through the medium in waves that Voyager is only now beginning to sample. One of the most scientifically productive aspects of Voyager's interstellar measurements has been what they reveal about the global shape of the heliosphere. Scientists have long known that the Sun moves through the galaxy at roughly 50,000 miles per hour relative to the local stellar neighborhood. This motion means the heliosphere is not a perfect sphere. The solar wind blows equally in all directions, but the solar system is plowing through the interstellar medium in one specific direction. The result is a structure shaped somewhat like a comet, a rounded nose pushing into the interstellar headwind on the leading side, and an elongated tail stretching out behind in the trailing direction. This tail, called the heliotail, may extend for hundreds of billions of miles far beyond what any spacecraft has explored or could explore in the foreseeable future. The shape of the heliosphere matters for life on Earth in ways that are not immediately obvious. The heliosphere acts as a shield against galactic cosmic rays, high-energy particles that originate from supernovae and other violent events throughout the galaxy. These particles carry enough energy to damage DNA and increase cancer risk in organisms exposed to them. Inside the heliosphere, the solar wind and the Sun's magnetic field deflect and scatter cosmic rays, reducing the flux that reaches the inner solar system and the Earth's surface. The Earth's own magnetic field provides additional shielding. The combination means that life on Earth is exposed to a small fraction of the cosmic ray flux that exists in unshielded interstellar space. If the heliosphere were smaller, or if the Sun were less active, or if the local interstellar medium were denser and more energetically active, the cosmic ray dose reaching Earth's surface would be higher, with potentially significant consequences for biological evolution and the incidence of radiation-related illness. Geological and fossil records suggest that periods in Earth's history, when the cosmic ray flux was higher, correlate with increases in genetic mutation rates and possibly with extinction events. The mechanisms are complex and contested, but the broad outline is clear. The state of the heliosphere is not irrelevant to the history of life on Earth. It is one of several factors, mostly invisible and mostly taken for granted, that set the conditions under which evolution has operated for billions of years. Voyager's measurements of the heliosphere's boundaries contribute directly to the scientific effort to understand these conditions and how they might vary over time. The plasma wave instrument on Voyager has produced what is perhaps the most publicly compelling finding of the entire mission beyond the initial planetary encounters, a detection that, when translated into sound, produces something genuinely eerie to human ears. In 2012, and again in 2020 and 2021, Voyager's plasma wave system detected oscillations in the interstellar plasma at frequencies that fall within the range audible to humans when the data is converted using standard sonification techniques. The instrument was not recording sound in any traditional sense. There is no air in interstellar space, no medium through which sound waves in the ordinary sense can propagate. What the instrument detected were oscillations in the electrical field of the plasma waves moving through the charged particles of the interstellar medium at the characteristic frequency of the plasma itself. When scientists converted these oscillations to audio, the result was a steady, low hum, persistent and unwavering, unlike the crackling and surging sounds that solar wind plasma produces inside the heliosphere. The interstellar hum is thin and faint and ancient. It reflects the natural resonant frequency of the plasma surrounding the spacecraft, a frequency determined by the density of the medium, by the magnetic field threading through it, by the accumulated effects of every energetic event that has disturbed this region of space over millions of years. It sounds, to human ears, like something between a mechanical drone and a natural tone, neither fully artificial nor fully organic. Scientists at Cornell University who led the analysis described it as a gentle, persistent plasma hum, and the description captures something of the quality. It is quiet, it is continuous. It does not rise or fall dramatically the way the sounds of the inner heliosphere do. It simply persists, the unbroken voice of the space between the stars. The detection of this hum provided a new method for measuring interstellar plasma density that complemented the solar storm oscillation technique used to confirm Voyager's crossing in 2012. The plasma frequency is directly related to the density of free electrons in the medium. By measuring the frequency of the hum precisely and applying the relevant equations from plasma physics, scientists could derive the electron density of the interstellar medium at Voyager's location with an accuracy that no earlier observation technique could approach. The values they obtained were consistent with, but more precise than, measurements made by observing how radio waves from distant pulsars are dispersed as they travel through the interstellar medium, a technique that averages over enormous distances and cannot easily resolve local variations. Voyager provided a point measurement, a single precise value at a known location, which could be compared against the pulsar dispersion average to reveal how much the local medium differs from the average. The answer is that the local interstellar medium is somewhat denser than average. The region of space that Voyager has entered since crossing the heliopause has an electron density roughly consistent with the warm, ionized component of the interstellar medium, the phase that exists at temperatures of around 10,000 degrees and pervades much of the volume of the galaxy. Between the clouds of cooler neutral gas, this phase is maintained by the ionizing radiation from hot stars scattered throughout the galaxy. Our Sun contributes to this ionization, as do the thousands of other stars within a few hundred light-years. The interstellar medium is not passive material sitting inert between the stars. It is a continuously processed substance, ionized and heated and stirred by the stars it surrounds, and it reaches back toward those stars in ways that influence their own behavior. The heliosphere exists inside this medium, shaped by it, and shaping it in return. The magnetic field in the interstellar medium that Voyager entered proved to be one of the most scientifically discussed aspects of the crossing. Before Voyager, scientists had predicted that the interstellar magnetic field in the region just outside the heliopause would be oriented in a particular direction. Based on observations of how magnetic fields align with interstellar structures elsewhere in the galaxy, and on models of how the heliosphere should interact with the surrounding medium, the prediction was specific enough to be testable. When Voyager's magnetometer data from beyond the heliopause was analyzed, the field direction turned out to be close to, but not exactly matching, the predicted orientation. The discrepancy was small but scientifically significant. Some of the discrepancy may reflect a genuine difference between what the models predicted and what the local interstellar field actually is, a finding that would require revisions to models of the galactic magnetic structure in this region. Some may reflect the fact that the heliosphere drapes the interstellar field around itself as it moves through the medium, distorting the field near the boundary from its undisturbed far-field orientation. Untangling these two effects requires measurements from multiple points in space, which is precisely what additional missions beyond Voyager would need to provide. The current Voyager data provides constraints on the problem, but cannot fully resolve it. The science remains open, which is to say, it remains alive. One of the persistent puzzles that Voyager's data has deepened rather than resolved concerns the energetic neutral atoms that the heliosphere produces. When solar wind ions strike neutral atoms drifting in from the interstellar medium, they can steal an electron, converting themselves from charged particles that cannot cross the heliopause into neutral atoms that can. These energetic neutral atoms travel in straight lines from their point of creation, since they carry no charge and respond to no magnetic field, and they can escape the heliosphere entirely, carrying information about the conditions at the point where they were created. A spacecraft that can detect these particles from a distance can effectively create an image of the heliosphere's boundary, mapping where the solar wind is most energetic, where the compression is greatest, where the heating is most intense. The IBEX mission, the Interstellar Boundary Explorer, launched in 2008 and has been creating exactly these maps from an orbit around Earth. The maps IBEX produced revealed an extraordinary feature that nobody had predicted: a bright ribbon of energetic neutral atom emission wrapping around the heliosphere in a great arc, seemingly aligned with the direction of the local interstellar magnetic field. The ribbon is roughly 2 to 3 times brighter than the surrounding emission, a clear and dramatic structure that stands out immediately from the data. Its origin has been the subject of intense scientific debate ever since. The most widely accepted explanation involves the interstellar magnetic field compressing and organizing the solar wind particles in the boundary region in a way that creates enhanced emission along specific directions. But alternative explanations have been proposed and have not been fully eliminated, and the structure of the ribbon continues to challenge modelers. The Voyager data and the IBEX data are complementary in a way that makes their combination more powerful than either alone. Voyager provides in-situ measurements, direct sampling of the plasma, the magnetic field, the particle populations at specific points in space. IBEX provides global imaging and overview of the entire heliosphere boundary structure seen from a distant vantage point. Neither can do what the other does. Together, they constrain theoretical models more tightly than either could alone, revealing where the models work and where they fail, identifying which physical processes are essential and which are secondary. Science progresses through exactly this kind of triangulation: different observations, different instruments, different vantage points, all converging on the same phenomena from different angles. The heliosphere's tail, the heliotail, remains almost entirely unexplored by direct measurement. Voyager 1 crossed the heliopause on the nose of the heliosphere, roughly in the direction the solar system is moving through the galaxy. Voyager 2 crossed somewhat off the nose, on the flank. Neither spacecraft is heading toward the tail, which extends in the direction the solar system has already come from. IBEX data has provided some information about the tail's structure from the energetic neutral atom maps, suggesting that it has a complex, cloverleaf-like cross-section rather than the smooth, elongated shape that simpler models predicted. But the tail extends so far that no spacecraft currently planned or funded is going to explore it in any detail that could reasonably be called direct. This geographic limitation of the existing data is a recurring theme in heliospheric science. What we know comes almost entirely from two trajectories, two lines drawn through a three-dimensional environment that spans hundreds of billions of miles. The knowledge gleaned from those lines is extraordinary, but the sampling is thin. Scientists do their best to extrapolate from 2 points to a whole surface, from 2 trajectories to a whole volume, from a handful of measurements to a complete physical picture. The extrapolations are informed by physical understanding and constrained by remote sensing observations, but they are still extrapolations. The uncertainty in the overall picture remains large, and the surprises that have come with every new phase of the Voyager mission are a standing reminder that the universe has a reliable habit of disagreeing with our models in ways we did not anticipate. Among the things that have most surprised scientists about the interstellar data is the nature of cosmic ray acceleration near the heliopause. Inside the heliosphere, energetic particles can be accelerated by multiple mechanisms: shocks in the solar wind, magnetic reconnection events, the termination shock itself. When particles are accelerated repeatedly by a series of shocks or magnetic disturbances, their energies increase with each interaction, a process called diffusive shock acceleration, and particles can reach very high energies by bouncing back and forth across a shock wave multiple times before escaping. The termination shock was expected to be a significant accelerator of anomalous cosmic rays particles that originated as neutral interstellar atoms, drifted into the heliosphere, became ionized by solar ultraviolet radiation, and were then picked up by the solar wind and swept outward to the termination shock, where they were expected to be accelerated to high energies. Voyager's measurements at the termination shock revealed something unexpected. The anomalous cosmic rays that scientists expected to find at their highest energies at the termination shock were not particularly energetic there. In fact, the highest energy anomalous cosmic rays appeared to come from somewhere beyond the termination shock, from deeper in the heliosheath, or possibly from the heliopause itself. The termination shock was doing some acceleration, but it was not the primary site. something in the heliosheath, or at the heliopause, was doing more. This finding required significant revisions to the models of cosmic ray acceleration in the heliosphere and opened new questions about the detailed structure of particle acceleration processes at the outer boundary. The implications extend beyond the heliosphere. The mechanisms that accelerate particles at the heliopause, whatever they turn out to be in detail, are related to the mechanisms that operate at the boundaries of other stellar systems, at the boundaries of supernova remnants, at the boundaries where stellar winds meet the interstellar medium around other stars. Every star with a significant stellar wind has a heliosphere-like structure, a bubble carved out of the surrounding medium by the pressure of the wind. Every one of those bubbles has a heliopause-like boundary where the wind meets the medium. Every one of those boundaries has, presumably, the same kinds of acceleration processes, the same kinds of magnetic reconnection events, the same kinds of particle physics that Voyager is sampling at our own heliosphere's edge. What we learn from Voyager applies in principle to every stellar system in the galaxy, to every bubble blown by every wind into every medium, to the fundamental processes by which the universe distributes energy among its particles. This is the quiet grandeur of the Voyager mission that is easy to miss in the day-to-day reports of instrument readings and power margins. The spacecraft did not travel to the edge of the solar system simply to measure the edge of the solar system. It traveled there to sample a class of physical processes that operates everywhere in the universe where energetic outflows meet surrounding media. The heliosphere is, in this sense, the nearest and most accessible example of a universal phenomenon. By studying it in detail, we gain insight into processes that shape the evolution of galaxies, the distribution of cosmic rays, the behavior of plasma on the largest scales in nature. Voyager's measurements have contributed to plasma physics, to cosmic ray physics, to magnetohydrodynamics, to the study of turbulence in magnetized media fields that extend far beyond the specific question of what happens at the edge of our solar system. Among the several instruments still operating on Voyager 1 as of the middle years of the 2020s, the magnetometer has perhaps provided the most persistently puzzling data. When Voyager crossed the heliopause in 2012, the magnetic field direction changed, but not as dramatically as expected. Inside the heliosphere, the solar magnetic field has been organized by the Sun's rotation into a spiral pattern, the Parker spiral, named after solar physicist Eugene Parker, who first described it mathematically in the late 1950s. This spiral is one of the well-established features of heliospheric physics, and Voyager had been moving through it for decades. Outside the heliopause, in interstellar space, the magnetic field should be oriented differently. It should reflect the local interstellar field, which has its own direction determined by galactic structure and the history of nearby supernova explosions. What the magnetometer found was that the field changed direction at the heliopause crossing, as expected, but the new direction was more nearly parallel to the heliopause surface than theory had predicted. Rather than the field lines in interstellar space being inclined at a substantial angle to the boundary, they ran almost along it. This finding has been interpreted as evidence that the interstellar magnetic field is being draped around the heliosphere as the solar system moves through the medium, the field lines piling up against the nose of the heliosphere and wrapping around its sides, much as a river's current flows around a large rock. If correct, this means that the interstellar field direction measured by Voyager near the heliopause is not the undisturbed far-field direction, but a locally modified version shaped by the presence of the heliosphere itself. To measure the true far-field direction would require a spacecraft that had traveled far enough from the heliopause to be beyond the region of field draping, a region that may extend for billions of miles into interstellar space. This possibility introduces an important caveat to all of Voyager's interstellar measurements. The spacecraft is not in undisturbed interstellar space. It is in the near heliosphere interstellar medium, the region immediately outside the heliopause, that is still influenced by the heliosphere's presence. The heliosphere modifies the surrounding medium through a variety of mechanisms. It deflects the interstellar flow, drapes the magnetic field, creates a bow wave or shock in the medium ahead of it as the solar system moves through the galaxy, and irradiates the surrounding medium with solar ultraviolet radiation. Voyager is sampling this modified region, not the pristine interstellar medium that exists far from any stellar influence. The measurements are enormously valuable, precisely because they come from this transitional zone, but their interpretation requires keeping in mind that the environment is not typical. Scientists have debated whether the solar system's motion through the interstellar medium is supersonic fast enough to create a genuine bow shock ahead of the heliosphere, analogous to the shock wave ahead of a supersonic aircraft. Earlier models generally assumed that a bow shock existed. More recent analysis of the interstellar field strength and plasma density suggests that the medium is stiff enough, the magnetic pressure high enough relative to the kinetic pressure of the flowing medium that the solar system may be moving through it at less than the magnetosonic speed, meaning no strong bow shock forms. Instead, there may be a gentler pileup of material ahead of the nose of the heliosphere, a compression without a sharp discontinuity. Voyager's measurements have provided data relevant to this question but have not fully resolved it, partly because the spacecraft crossed the heliopause on the nose rather than traveling ahead of it into the undisturbed bow wave region. The question of the bow shock is not merely academic. Whether or not a strong shock exists affects the degree to which cosmic rays and interstellar neutrals are organized and processed before they enter the heliosphere. It affects the shape of the heliosphere's nose and the dynamics of the heliopause boundary. It affects how the heliosphere will respond to changes in the interstellar medium changes that are coming, according to current trajectories, as the solar system moves through the local bubble and approaches regions of the interstellar medium with different properties. The solar system has been moving through the local fluff for tens of thousands of years. Models suggest it may exit the local fluff within the next few thousand years and enter a denser, cooler region of the local interstellar medium. If that transition occurs, the heliosphere's size and shape will change, potentially significantly, and the cosmic ray shielding it provides to the inner solar system will change with it. Whether those changes would matter for life on Earth is a question that researchers are beginning to take seriously. The solar system has moved through many different interstellar environments over its 4.5 billion year history, some denser and cooler than the current local medium, some rarer and hotter. Each environment would have produced a heliosphere of different size and shape, with different shielding properties. Periods when the heliosphere was compressed by a denser interstellar medium would have exposed the inner solar system to higher cosmic ray fluxes. Whether those exposures left detectable marks in the geological record, in isotope ratios in ancient rocks, in the record of genetic mutation rates preserved in the fossil record, is an active area of research. Voyager's measurements of the current heliosphere and its boundaries provide the baseline data for this research, the modern reference point against which ancient variations can be compared. The radioactive isotope beryllium 10 is produced when cosmic rays strike nitrogen and oxygen atoms in the upper atmosphere. It accumulates in ice cores and marine sediments at rates that reflect the cosmic ray flux reaching Earth. By measuring beryllium 10 concentrations in ancient ice cores drilled from the Antarctic and Greenland ice sheets, scientists can reconstruct the history of cosmic ray exposure going back hundreds of thousands of years. The record shows variations that track the Sun's activity cycle, the reversals of Earth's magnetic field, and possibly variations in the heliosphere's shielding effectiveness. Longer records from ocean sediment cores extend the reconstruction further back in time. The pattern that emerges is one of continuous variation, with no extended periods of dramatically elevated or reduced cosmic ray flux that would suggest a major change in interstellar environment within the past few million years. The local interstellar medium has apparently been reasonably stable over this period, and the heliosphere has maintained roughly its current scale. But the stability is not guaranteed to continue, and understanding it requires the kind of direct measurements that only Voyager has ever provided. The power budget that constrains Voyager's remaining operating life has been managed with extraordinary care over the decades since launch. Each decision to disable a component or reduce a heater involves careful analysis of the trade-offs: less power available for science instruments, but instruments better preserved against the cold. Some instruments powered down permanently, but others kept alive for measurements that cannot be replicated. The engineers who made these decisions in the 1990s and 2000s were often the successors of the original mission team, brought in to continue work begun by colleagues who had retired or passed away. Managing Voyager across generational transitions in the engineering team has required exceptional documentation and institutional knowledge transfer. Aspects of long-duration mission management that the planetary science community has learned from and tried to apply to subsequent missions. In October 2023, Voyager 1 began returning corrupted data from one of its 3 onboard computers, the Flight Data System, which is responsible for packaging scientific and engineering data for transmission to Earth. The data that reached the ground was repetitive and unreadable, suggesting that the computer was stuck in a loop, writing the same meaningless pattern over and over rather than collecting and transmitting real measurements. For months, mission engineers received no usable science data from the spacecraft. The team spent weeks analyzing the problem from a distance of more than 15 billion miles, a challenge of almost surreal difficulty diagnosing a computer malfunction using only the garbled outputs that malfunction was producing. On a 46-year-old spacecraft whose repair manuals existed only in archived paper documents and the memories of senior engineers. The diagnosis, when it finally came, pointed to a single memory chip that had failed, corrupting the portion of the flight data system's code stored in that chip's memory location. The engineers could not replace the chip. They could not directly access the hardware. What they could do, with extraordinary care and ingenuity, was devise a way to route the corrupted code section around the failed chip by distributing it across other available memory locations on the spacecraft, a software patch transmitted across 15 billion miles of space, requiring 22 hours for the command to arrive, and another 22 hours for the confirmation to return, each iterative test taking nearly 2 days to evaluate. By April 2024, after months of this painstaking remote repair work, Voyager 1 was again returning usable science data. The team had, in effect, performed open-heart surgery on a computer built in the 1970s from a distance of 15 billion miles, using programming techniques that the original designers had never anticipated would be needed. The successful repair was a moment of quiet triumph that received far less public attention than it deserved. It demonstrated that the Voyager mission had not simply been maintained over nearly 5 decades through luck and inertia. It had been actively sustained by generations of engineers who brought real intelligence and dedication to the challenge of keeping an aging, remote, irreplaceable spacecraft alive and productive. The knowledge these engineers accumulated about the spacecraft's quirks, its failure modes, its margin of safety, the way its aging systems behave under different conditions is itself a kind of scientific and engineering treasure, accumulated over decades through a process that cannot be rushed or replicated from scratch. The broader story of Voyager's longevity raises questions about the future of deep space exploration that go well beyond the specific mission. How do you plan for a 50-year mission when the engineers who will be responsible for it in year 45 are not yet born when the mission launches? How do you document a spacecraft's behavior comprehensively enough that successors can work on it without having been there from the beginning? How do you maintain institutional knowledge across retirements, deaths, budget cycles, agency reorganizations, and shifts in scientific priorities? These are not merely management questions. They are questions about how scientific institutions sustain long-term commitments in a world that tends to think in shorter cycles. Voyager's history of successful management through these challenges has informed how other long-duration missions are designed, documented, and planned, even if the specific answers that worked for Voyager cannot always be transferred directly to different programs with different constraints. The scientific community has begun planning seriously for successor missions to Voyager missions explicitly designed to go beyond the heliosphere and conduct systematic, comprehensive measurements of interstellar space, rather than the opportunistic measurements that Voyager has made with instruments not designed for the purpose. These discussions intensified in the early 2020s as it became clear that Voyager's remaining operational life was measured in years rather than decades. The specific mission concepts vary in their details. Some favor a large flagship spacecraft with a comprehensive instrument suite. Others prefer swarms of smaller, cheaper probes distributed across multiple trajectories to sample the heliosphere and nearby interstellar space at multiple points simultaneously. All of them face the same fundamental challenge that has constrained deep space exploration since the beginning: Reaching interstellar distances with conventional chemical or nuclear electric propulsion takes decades, and sustaining a mission for decades requires sustained institutional and financial commitment of a kind that has historically been rare. The interstellar probe concept that NASA's Planetary Science Decadal Survey considered in the early 2020s envisioned a spacecraft launched in the 2030s, capable of reaching the heliopause in roughly 15 years rather than Voyager's 35, using a combination of advanced propulsion and a solar gravitational assist. By flying close to the Sun, very close, within a few solar radii of the photosphere, and firing its engines at the point of closest approach, when its solar-boosted velocity is at maximum, the spacecraft could achieve a speed of roughly 10 times Voyager's current velocity. In principle, it could reach the heliopause before the scientific teams who designed it had retired. In principle, the technical challenges of building a spacecraft capable of surviving a close solar pass, and the funding challenges of getting such a mission approved and resourced through a multi-decade development and flight program, remain formidable. The science that such a mission could accomplish goes well beyond simply repeating what Voyager has already done. An interstellar probe designed with modern instruments and launched on a trajectory specifically chosen to sample the most scientifically interesting parts of the heliosphere and nearby interstellar space could return data of a quality and Mises Pacis Far-Jan comprehensiveness that would transform the field. It could map the magnetic field throughout the heliosheath with far more detail than Voyager's single trajectory sampling. It could measure the composition of interstellar dust grains directly, identifying the solid material that drifts between the stars and eventually contributes to the formation of new planetary systems. It could sample the isotopic composition of the interstellar medium in detail that spectroscopic observations from Earth cannot approach. It could characterize the plasma wave environment of interstellar space with high-fidelity instruments rather than the aging, limited systems that Voyager carries. It could, in short, turn what Voyager began into the foundation of a real scientific discipline, interstellar in-situ measurement, rather than a single extraordinary but limited precedent. The instruments available to a modern mission would themselves be enormously more capable than what Voyager carries. Miniaturization has transformed scientific instrument design since 1977. Instruments that filled entire racks of electronics in the 1970s can now be built into packages the size of a thick book, using far less power and producing data at far higher rates. Modern magnetometers are more sensitive, more stable, and more immune to spacecraft electromagnetic interference than their 1977 counterparts. Modern plasma analyzers can measure particle energy distributions with finer resolution across a broader energy range. Modern computers can perform onboard data processing that would have required ground-based supercomputers in Voyager's time, allowing the spacecraft to transmit compressed, processed science products rather than raw instrument readings, effectively multiplying the information content of each transmitted bit. A modern interstellar probe, with the benefit of 40 years of instrument development, would not be incrementally better than Voyager. It would be categorically different. The case for an interstellar probe rests not just on the scientific questions that remain unanswered, but on the nature of those questions themselves. They are not narrow or specialized. They touch on some of the most fundamental aspects of our understanding of the solar system's place in the galaxy, of the conditions that made life possible on Earth, of the physics that governs plasma and magnetic fields and particle acceleration across the entire observable universe. They are questions that matter beyond the community of planetary scientists and heliospheric physicists who study them professionally. They matter to anyone who has ever looked up at the night sky and wondered what lies out there, beyond the familiar neighborhood of planets and moons and asteroids in the vast dark between the stars. The heliosphere is not incidental to the story of life on Earth. It is part of that story in ways that took decades of research to begin appreciating. Every organism that has ever lived on this planet has done so inside the heliosphere, benefiting from the shielding it provides against the full flux of galactic cosmic rays. The evolution of complex life, the development of the biosphere from its earliest microbial forms to the extraordinary diversity that exists today, has taken place under conditions partly set by the sun's stellar wind and the bubble it carves in the surrounding medium. The The heliosphere is not a passive backdrop to the story of life. It is a character in it, one whose behavior over billions of years has helped determine what kinds of organisms could survive and evolve, and eventually build spacecraft to go and look at it directly. Understanding the heliosphere thus connects to the deepest questions in astrobiology, the study of life's relationship to its cosmic environment. When scientists search for habitable worlds around other stars, they look for planets in the right temperature range, with the right atmospheric compositions, with liquid water on their surfaces. These are necessary conditions, but they are not sufficient. A planet can have all of these properties and still be uninhabitable if its star does not provide adequate shielding against cosmic rays, or if the local interstellar medium is dense enough that the stellar wind cannot carve a protective bubble large enough to shelter the planet's orbit. The heliosphere of our solar system is a model for what stellar wind bubbles look like and how they function. Understanding our own heliosphere in detail provides the scientific framework for assessing whether the heliospheres of other stars can support the conditions for complex life on their planets. Exoplanet science has expanded enormously over the past 2 decades. We now know that planets are extraordinarily common around other stars. The galaxy contains more planets than stars, perhaps many more, and a significant fraction of them orbit at distances that place them in the temperature range for liquid water. The number of potentially habitable planets in the galaxy, by a conservative estimate, runs to billions. The question of which of them actually harbor life, and which harbor the kind of complex multicellular life that could develop technology and eventually ask these questions, depends on factors that go far beyond surface temperature and atmospheric composition. It depends on stellar activity, on magnetic field strength, on the local interstellar environment, on the history of cosmic ray exposure over billions of years. All of these factors involve physics that is directly related to the heliospheric physics that Voyager has been illuminating. The connection runs even deeper when you consider the role of cosmic rays in biological evolution. Cosmic rays are mutagenic. They cause strand breaks in DNA. At the doses that would exist without heliospheric shielding, the mutation rate in surface-dwelling organisms would be substantially higher than it is in the current shielded environment. Higher mutation rates drive faster evolution. They also cause more cancer, more genetic disease, more developmental errors. Whether the net effect is positive or negative for the development of complex life is not straightforward. Evolution requires mutation, but too much mutation is lethal. The current cosmic ray environment, filtered by the heliosphere, may represent something close to an optimal mutation rate for the development of complex life high enough to drive evolutionary innovation over geological timescales, low enough that organisms with sophisticated DNA repair mechanisms can survive and reproduce successfully. If the heliosphere were smaller, or the local interstellar medium more energetic, the cosmic ray dose would be higher, the mutation rate would increase, and the evolutionary dynamic would be different. Whether complex life could still arise under those conditions is genuinely unknown. Voyager's measurements of the heliosphere's shielding properties at its boundaries, the cosmic ray gradients across the termination shock and heliopause, the particle populations in the heliosheath, contribute directly to the scientific effort to understand what range of heliospheric conditions are compatible with the development of complex life. This is not speculation. It is a research program with real scientific content, and Voyager's data is part of its foundation. There is another aspect of what Voyager detected at the edge of the solar system that deserves careful attention, one that has received less public discussion than the dramatic findings about plasma temperatures and magnetic reconnection and the interstellar hum. That aspect is silence the specific character of the quietness that Voyager encountered when it crossed the heliopause and entered interstellar space. Inside the heliosphere, the plasma wave instruments on Voyager recorded a continuous, complex noise environment. Solar wind turbulence, shocks from coronal mass ejections, particle beam interactions, wave-particle resonances, all of these produced a rich electromagnetic soundscape that varied continuously with the Sun's activity and with Voyager's distance from it. The heliosphere is acoustically rich if you translate its electromagnetic oscillations into sound. It hisses and crackles and hums and occasionally roars with the violence of solar events. Beyond the heliopause, that richness largely disappeared. The interstellar medium, at least in the local region that Voyager has sampled, is quieter. Not completely silent, the plasma hum that scientists detected represents a low-level background oscillation that persists continuously. But the dynamic range of the electromagnetic environment is much smaller. The intense bursts of wave activity that characterize the inner heliosphere are absent. The passage of solar storms, which produce detectable wave signatures at Voyager even when the spacecraft is billions of miles from the Sun, becomes less and less perceptible as Voyager travels deeper into interstellar space. The interstellar medium, at least locally, is a calmer electromagnetic environment than the solar wind region. The storms of the heliosphere do not reach far beyond the heliopause. What lies beyond is not the complete stillness of empty space, but it is vastly quieter than the turbulent interior of the solar system's bubble. This quietness has a quality that is worth dwelling on, not because it is scientifically dramatic in itself, but because it speaks to the nature of the environment that lies beyond everything we have ever directly explored. The solar system, for all its scale, is a noisy, energetic, electromagnetically active place. The Sun drives it constantly, pumping energy into every corner of the heliosphere, driving winds and shocks and wave activity across billions of miles. Step outside the heliopause, and you leave that driven environment behind. You enter a medium that is maintained by entirely different energy sources, cosmic rays from distant supernovae, the residual radiation of the Big Bang, the slow processing of interstellar material by the ultraviolet radiation from all the stars in the galaxy simultaneously. It is not a passive environment, but it operates on different timescales with different drivers in a different energy regime. Voyager's instruments, designed to measure solar wind phenomena, have detected its quieter rhythms. And those rhythms tell a story about the universe that no telescope looking from the inside of the heliosphere could ever fully reveal. The story of what happened to Voyager 2 at the heliopause deserves its own careful telling, because the comparison between the two crossings is scientifically essential, and the differences are illuminating in ways that matter for the overall picture. Voyager 2 crossed the heliopause in November 2018, 6 years after Voyager 1, at a different location on the heliosphere's surface and on a different trajectory. The crossing was detected by similar signatures: a sharp increase in cosmic ray flux, a sharp decrease in solar wind particle counts, changes in the magnetic field direction, but the detailed character of the crossing differed from what Voyager 1 experienced in ways that immediately told scientists something important about the boundary. The heliopause that Voyager 2 crossed was thinner. The transition from heliospheric to interstellar conditions was sharper, occurring over a shorter distance. The magnetic field compression at the boundary was higher, suggesting that the pressure balance between the solar wind and the interstellar medium was different at Voyager 2's crossing point than it had been at Voyager 1's crossing point 6 years earlier. Some of this difference may reflect different local conditions along the two trajectories. The heliopause surface is not uniform, and different regions may have different properties. Some may reflect changes in the Sun's activity between the two crossing times. The Sun goes through an 11-year activity cycle, and the two crossings occurred at different phases of this cycle, which affects the solar wind pressure pushing outward against the heliopause. Untangling these two contributions requires careful modeling and has not been fully accomplished. One finding from Voyager 2's crossing that was completely unexpected was the detection of a thin layer of hot plasma just inside the heliopause. This layer, only a few 100 million miles thick, negligible on the scale of the heliosphere as a whole, but clearly real in the data, was substantially hotter than the surrounding heliosheath plasma. It appeared to be a region where plasma from the inner heliosheath was compressed and heated by contact with the heliopause boundary in a way that created a distinct thermal structure. Nothing in the models had predicted this layer with any specificity. When scientists went back to look at Voyager 1's data from its heliopause crossing, they found hints of a similar structure, but less clearly resolved in that dataset. The Voyager 2 crossing gave clearer evidence for something that the models had missed entirely, something that reflects the detailed physics of how a supersonic stellar wind comes to rest against an external pressure boundary. The plasma instruments on Voyager 2 functioned better at the heliopause crossing than those on Voyager 1 had in 2012. By the time of Voyager 1's crossing, the plasma science instrument on that spacecraft had been non-functional for years, a victim of the same instrument mortality that had claimed other systems over the decades of the mission. Voyager 2 retained its plasma science instrument in working order through its crossing, providing direct measurements of the solar wind speed, density, and temperature that Voyager 1 could not supply at the equivalent moment. These measurements allowed scientists to determine precisely when the solar wind speed dropped to zero at the heliopause, and to characterize the plasma on both sides of the boundary with a completeness that the Voyager 1 data could not match. The two crossings together, with their different instrument complements and different trajectories, provide a richer dataset than either alone could offer. The findings from both crossings have substantially changed how scientists think about the heliopause as a physical structure. Earlier models imagined it as a relatively thin, sharp boundary, almost a surface that the solar wind could not penetrate and the interstellar medium could not breach. The data shows something more complex. The heliopause is a region, not a line. It has thickness. It has internal structure. Material leaks across it in both directions, not in bulk, but in the form of energetic particles and neutrals that can cross through processes involving charge exchange and magnetic reconnection. The boundary is permeable to some particles and impermeable to others, depending on their energy and charge state. It is dynamic, moving in and out in response to solar activity and interstellar pressure variations. It is not a wall. It is a membrane, a living, breathing, constantly renegotiated interface between two vast physical environments. This reconceptualization of the heliopause has implications for how we think about the solar system's relationship to its galactic environment. If the boundary is genuinely permeable to some particle populations, then the solar system is not as isolated from the interstellar medium as simpler models suggested. Material from the interstellar medium leaks inward across the heliopause and eventually reaches the inner solar system, where it can interact with solar wind particles, become incorporated into the clouds and debris that fill interplanetary space, and possibly reach the inner planets. The amount of interstellar material that penetrates the heliosphere is small compared to the solar wind, but it is real and measurable. Interstellar dust grains have been detected inside the heliosphere by in situ instruments and by the Ulysses spacecraft. Interstellar neutral atoms stream through the heliosphere and can be detected from Earth orbit when they become ionized by solar radiation and are swept up by the solar wind. The composition of this infiltrating interstellar material provides a direct sampling of the local interstellar medium that complements Voyager's in situ measurements from outside the heliopause. By combining the analysis of interstellar material detected inside the heliosphere with Voyager's measurements of conditions just outside the heliopause, scientists are building a composite picture of the local interstellar environment with a richness that neither source of data could provide alone. The picture that emerges confirms the general outline that models had suggested the local medium is warm, partially ionized, magnetically structured, and moving relative to the solar system at a speed that is probably below the magnetosonic speed for the medium's properties. But the details continue to surprise and to challenge the models in ways that keep the field scientifically productive. One of the most profound aspects of the Voyager story, and one that tends to get lost in discussions focused narrowly on instrument readings and physical measurements, is what the mission reveals about the relationship between human timescales and cosmic timescales. The heliosphere has existed for as long as the Sun has existed, roughly 4.5 billion years. It has been shaped by interstellar environments that have changed enormously over that period. The solar system formed in a molecular cloud that no longer exists. It moved through regions of the galaxy that contain denser gas, hotter plasma, stronger magnetic fields, higher cosmic ray fluxes. It passed through the aftermath of nearby supernova explosions that temporarily deformed the heliosphere and flooded the inner solar system with elevated cosmic ray fluxes. All of these events are recorded faintly in the geological record of the Earth and in the chemical record of meteorites and cosmic dust preserved in asteroid material. Voyager has been operating for roughly 50 years, a fraction of a percent of the solar system's history, a blink of an eye on any cosmic timescale. In those 50 years, it has traveled roughly 160 astronomical units from the Sun, a tiny distance compared to the 4 light-years to the nearest star, negligible compared to the tens of thousands of light-years to the galactic center. And yet in those 50 years, covering that tiny fraction of the distance to the nearest star, Voyager has fundamentally transformed our understanding of the solar system's outer boundary and its relationship to interstellar space. This is partly because the boundary is close, as cosmic distances go, and partly because the physics is rich enough that even limited sampling reveals essential features. But it is also because the measurements were made with persistence, with patience, with the willingness to keep listening to a faint signal from a small machine over decades, long after the initial excitement of the planetary encounters had faded. Patience is perhaps the most underrated virtue in science. Voyager's most important discoveries did not come during the dramatic planetary flybys of the early 1980s, when images of Jupiter's moons and Saturn's rings dominated magazine covers and television broadcasts and gave the mission its public identity. They came decades later, when the spacecraft was far from any planet, when the instrument readings were subtle and their interpretation required years of careful analysis, when the team responsible for the mission was a fraction of its original size and operated on a fraction of its original budget. The discoveries at the heliopause came because people kept paying attention. They kept analyzing. They kept refining the models and checking the calibrations and arguing over interpretations. Science at its best is a long conversation carried on across generations, and Voyager's story is a demonstration of that process at its most extended and most productive. The broader human meaning of the Voyager mission is something that different people find in different places. Some find it in the golden record, in the gesture of reaching out across the cosmic dark with music and images and greetings, in the statement that humanity valued contact with whatever else might exist in this universe enough to engrave the attempt in gold and launch it toward the stars. Some find it in the engineering and the audacity of building machines that have outlasted their designers, that have operated continuously for nearly 5 decades in the harshest environment accessible to human technology, that have communicated across distances that stagger the imagination. Some find it in the science, in the specific findings about plasma temperatures and magnetic reconnection and the interstellar hum, in the revision of models and the opening of new questions, in the contribution to the human effort to understand the universe on its own terms. And some find it in the perspective that the Voyager mission offers on the place of our solar system in the galaxy. Before Voyager, the heliosphere was a theoretical construct, something scientists had inferred from indirect evidence and modeled on paper but had never directly explored. Voyager made it real. It showed that the solar system exists inside a bubble, a protected region carved out by the sun's own output, bounded by a dynamic and complex interface, surrounded by an interstellar medium that is itself a structured and active physical environment. It showed that the solar system is not an island in empty space, but a participant in the ongoing physical processes of the galaxy, buffeted by interstellar winds, irradiated by cosmic rays from distant catastrophes, magnetically connected to the broader structure of the galactic medium. We live inside something. That something has boundaries. And those boundaries are stranger and richer and more alive with physical activity than anyone imagined when 2 spacecraft were assembled in California and aimed at the dark. The question of what lies beyond Voyager's current position, what the interstellar medium looks like farther from the heliopause, how it varies across distances measured in light years rather than astronomical units, what structures and environments the solar system will encounter as it continues its orbit around the galactic center, remains almost entirely unanswered by direct measurement. The instruments that can address these questions from Earth are powerful, but indirect. Radio telescope observations of pulsars measure the integrated electron density along lines of sight that pass through enormous volumes of the interstellar medium, providing averages that smooth out all local variations. Optical and ultraviolet spectroscopy of nearby stars traces the composition and velocity of interstellar gas clouds along specific sight lines, providing chemical information but limited spatial resolution. X-ray observations reveal the hot, tenuous gas that fills the local bubble and similar structures, but cannot resolve the detailed structure of cooler, denser clouds. All of these methods are valuable. None of them are the same as being there. The scientific community that works on heliospheric and interstellar physics is a small but deeply dedicated group. The names that appear repeatedly in the scientific literature on Voyager's heliopause crossing and interstellar measurements represent careers that have been built, in some cases, entirely around the data that these two spacecraft have returned. There are scientists who have spent 30 years analyzing Voyager data and who regard the spacecraft with something approaching personal affection, not in a way that compromises their objectivity, but in the way that anyone might regard a companion who has been with them through the most important work of their professional life. The spacecraft are not alive, of course. But they have personalities in the engineering sense: quirks, behaviors, characteristic responses to changing conditions that only people who have worked with them for decades fully understand. The institutional knowledge embedded in the Voyager science and operations team is irreplaceable, and its gradual loss as team members retire and age is one of the quiet tragedies of the mission's waning years. The engineers and scientists who have kept Voyager operating across 5 decades have done something more than maintain a spacecraft. They have maintained a commitment to the idea that knowledge gained at great distance and over great time is worth the sustained effort to acquire it. They have demonstrated that institutions can sustain long-term scientific programs when they have the will and the resources to do so. They have shown that the returns on patience in science can be extraordinary. What Voyager found at the edge of the solar system could not have been predicted in 1977 and could not have been discovered any other way. It required going there. It required staying there. It required listening for decades to a faint signal from a distant machine that had no business still working and kept working anyway. There's a philosophical dimension to this that goes beyond the science itself. The Voyager mission began as an act of exploration, a decision to send instruments into the unknown because the unknown had value, because understanding was worth pursuing even when its practical applications were unclear. The mission has repaid that decision with discoveries that have transformed planetary science, heliospheric physics, plasma physics, cosmic ray physics, and astrobiology. Some of those discoveries have potential practical applications: better models of cosmic ray exposure matter for predicting astronaut radiation doses on deep space missions, for protecting satellites, for understanding climate connections. But these applications were not the primary motivation for the mission, and they could not have been predicted in advance with any specificity. The decision to explore was made on general principles, and the specific returns have exceeded any specific expectation. This patterned broad investment in exploration returning specific knowledge whose value exceeds the investment has characterized the history of space science repeatedly. It characterized the discovery of the Van Allen radiation belts, which nobody predicted before Explorer 1 found them in 1958. It characterized the discovery of Jupiter's volcanic moon Io, which nobody expected before Voyager 1 photographed it in 1979. It characterized the discovery of liquid water beneath the ice of Europa and Enceladus, which has transformed the search for life in the outer solar system. It characterized the discovery of the interstellar hum and the anomalous temperature structure of the heliosheath that Voyager made at the boundary of everything we had previously explored. Exploration returns surprises. Surprises are where the most important knowledge lives. The willingness to go into the unknown and observe carefully is the single most reliable investment that science can make. The spacecraft themselves, whatever they detect or fail to detect in their remaining operational years, have already secured a permanent place in the story of human exploration. They are the most distant human-made objects in existence. They will remain so for decades, possibly for centuries, given the current pace of space exploration. When the last signal finally fails, when the power drops below the threshold needed to maintain the transmitters, when the last instrument falls silent, when the last data packet arrives at Earth and is processed and archived, the spacecraft will not stop. They will keep moving. They will drift outward into interstellar space at roughly 35,000 miles per hour, covering about 1 billion miles per year for billions of years. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of a small red dwarf star called Gliese 445, currently in the constellation Camelopardalis. It will not be captured by that star's gravity. It will drift past and continue outward, carrying its golden record and its silent instruments into a darkness that will last far longer than the civilization that created it. This thought that Voyager will outlast humanity by an enormous margin, that it will be drifting through the galaxy long after every building we have constructed has crumbled, long after every language we have spoken has been forgotten, long after the sun itself has expanded into a red giant and consumed the inner solar system, is simultaneously humbling and oddly comforting. The universe is indifferent to us, certainly. The darkness that Voyager moves through does not know or care about its passage. But the spacecraft carries with it the evidence that intelligence existed here, that a species arose on a small planet orbiting an ordinary star and decided to reach outward beyond everything it knew, and that the reaching produced knowledge, and that the knowledge was worth having. The golden record that Voyager carries is unlikely ever to be found by another intelligence. The galaxy is vast, and spacecraft are small, and the odds of an accidental encounter over any human timescale are essentially zero. It was sent not as a practical communication, but as a philosophical gesture, a statement about the kind of beings we aspire to be: curious, and reaching, and willing to announce our existence to a universe that may or may not be listening. The scientific instruments on Voyager were the practical complement to that gesture, the real communication, not with hypothetical aliens, but with ourselves, returning data that expanded our self-understanding, that told us where we live and what surrounds us, and what our solar system's place in the galactic order actually is. What Voyager found at the edge of the solar system is not simply a set of measurements. It is an answer to a question so basic that it had rarely been asked explicitly before the mission forced it. What does the solar system's boundary actually look like? The answer turned out to be far more complex, far more dynamic, far more physically rich than any model had predicted. The boundary breathes. It fluctuates with the sun's activity. It wrinkles and ripples in response to interstellar pressure variations. It is permeated by magnetic reconnection events that heat the surrounding plasma to temperatures higher than anything in the solar wind. It is threaded by a magnetic highway that mixes solar and interstellar particles in a region that should not exist according to the simplest models. It hums with the resonant frequency of the plasma that surrounds it. And beyond it, in the interstellar space that Voyager now moves through, the universe continues its business with complete indifference to the small machine sampling it. Stars are being born in molecular clouds hundreds of light years away. Stars are dying in supernova explosions that will enrich the interstellar medium with heavy elements. Cosmic rays are being accelerated in the shock waves of expanding supernova remnants and are streaming across the galaxy, some of them heading toward our solar system, where they will be deflected or absorbed by the heliosphere. Magnetic fields are being twisted and reconnected. Plasma clouds are drifting and colliding. The galaxy is alive with processes that have been operating for 13 billion years and will continue for billions more. Voyager moves through the edge of all of this at 35,000 miles per hour, which is a remarkable speed by human standards and a negligible speed by galactic standards. It will never reach another star. It will never encounter another planet. It will drift through the interstellar medium for longer than the current age of the solar system before it comes close to anything. In that sense, its journey is just beginning a phase that no instrument will be alive to document, a journey into a silence that no signal will cross. The scientific mission will end within years. The physical journey will end never. The last data Voyager will ever send home will be measurements of something, perhaps the plasma density of the interstellar medium at a particular location, perhaps the magnetic field direction at a moment when a cosmic ray event perturbs it slightly. Perhaps a reading of particle energies as a stream of galactic cosmic rays passes through the spacecraft's detectors. Whatever the last measurement is, it will be followed by silence. Not the dramatic silence of a mission that failed suddenly, but the gradual silence of diminishing power, of signals too weak to detect, of a machine that worked faithfully for longer than any human institution typically manages to sustain anything, going quiet in the dark. Scientists at the Jet Propulsion Laboratory estimate that by the late 2020s, the power level will be too low to operate any science instrument with confidence. By the early 2030s, the transmitters themselves may fall below reliable operation thresholds. The exact timing depends on how the remaining power systems perform. Radioisotope thermoelectric generators do not fail abruptly. They decline slowly, and the precise rate of decline has some uncertainty. The mission team will make every effort to extract every last useful measurement before the inevitable end. They will prioritize ruthlessly, powering down everything that is not essential to the most irreplaceable measurements. They will squeeze the science budget of every subsystem down to absolute minimum levels. They will do what they have always done: find a way to keep the data coming a little longer, to push the boundary of what seemed possible a little further. And then it will be over. The spacecraft will continue on its trajectory, indifferent to its own silence, carrying the mathematical equations that describe its location through any given moment with perfect precision. Anyone who wants to know where Voyager is in 10,000 years can calculate it from the known physics. The spacecraft will be found by the equations to be at a predictable location, moving in a predictable direction, at a predictable speed. The trajectory of a machine in interstellar space, with no significant gravitational perturbations for light years in any direction, is one of the most precisely knowable things in the physical universe. Long after the signal is gone, the position is calculable. What will not be calculable is what the spacecraft might have measured if it had reached the next significant boundary in the interstellar medium, the edge of the local fluff, where the warm, partially ionized cloud our solar system currently inhabits gives way to a different interstellar environment. That boundary may lie only a few thousand astronomical units beyond where Voyager will fall silent, or it may lie much farther. The uncertainty reflects the limits of remote sensing observations that sample that region from Earth. A functioning Voyager might have reached it in a century or two. A future mission with better propulsion might reach it in decades. For now, it remains unmeasured, another boundary waiting for the instruments that will eventually cross it. The legacy of what Voyager found at the edge of the solar system will endure long after the spacecraft falls silent, just as the legacy of other foundational scientific observations endures long after the instruments that made them have been retired. The measurements Voyager returned the plasma temperatures, the magnetic field directions, the cosmic ray gradients, the particle populations, the plasma wave frequencies have been archived, analyzed, published, and incorporated into the scientific literature in hundreds of papers spanning decades. They are part of the permanent scientific record. Future researchers will return to them, as they return to all foundational datasets, using new analysis techniques, asking new questions, finding new answers in data that seemed fully analyzed when first collected. This is the nature of good scientific data. It does not exhaust itself. Each generation of scientists brings new methods and new theoretical frameworks that extract new meaning from old measurements. The Voyager data from the planetary encounters of the early 1980s is still being analyzed today, still yielding new findings about Jupiter's magnetosphere and Saturn's ring system, and the geology of the outer moons. The heliospheric and interstellar data that Voyager returns today will be analyzed for decades after the mission ends. As new missions provide context, as new theoretical models develop more detailed predictions, as new analytical tools make it possible to extract information that was buried in the data but not accessible to the methods available when the measurements were first made. The deep human need that space exploration serves is not simply curiosity, though curiosity is part of it. It is the need to locate ourselves, to understand where we are, what surrounds us, what the context of our existence actually looks like when examined rather than assumed. Every civilization throughout history has constructed cosmologies, models of the universe, and the solar system's place in it because the need to understand the context of existence is fundamental to what it means to be a thinking being. Modern science has replaced mythological cosmology with empirical cosmology, has replaced stories about the cosmos with measurements of the cosmos, but the underlying need is the same. We need to know where we are. Voyager has told us, more directly than anything ever has, what the immediate cosmic neighborhood looks like. It has shown us that we live inside a bubble blown by our own star, a bubble bounded by a complex and dynamic interface with the interstellar medium, surrounded by a galaxy that is vast and energetic and old and indifferent. It has shown us that the boundary of our home is not a wall but a membrane, not static but breathing, not simple but extraordinarily rich, with physical processes that operate on scales from individual particle interactions to structures spanning the entire solar system. It has shown us that the space beyond the boundary, the interstellar space that extends to the nearest stars and beyond, is not empty darkness, but a thin and structured medium permeated by magnetic fields and cosmic rays and the echoes of ancient explosions. This is knowledge, not comfort necessarily, not the reassurance of a friendly cosmos waiting to welcome us. The universe does not offer that. What it offers, to those who look carefully enough, is understanding. And understanding, earned through the patient work of building instruments and launching them, and listening to their signals for decades, and analyzing their data with rigor and honesty, is one of the most distinctly human things there is. Two machines launched in 1977, built by human hands from human materials, guided by human mathematics, and sustained by human dedication, have traveled farther from Earth than anything made on this planet has ever gone. They have sampled the edge of everything we call home. They have found that the edge is stranger and more alive than we imagined. And they have sent their findings back across 13 billion miles in a signal carrying less power than a light bulb, arriving after a journey of 22 hours to instruments built to listen for exactly that whisper. The whisper says, "The universe is not what you thought. It is more complex. It is more energetic. It is more dynamic. The boundary of your solar system is a living thing, breathing with the sun's activity, wrinkled by the pressure of the interstellar wind, heated by the constant violence of magnetic reconnection, humming with the resonant frequency of the plasma that surrounds it. Beyond that boundary, in the quiet of interstellar space, the galaxy continues its ancient business stars forming and dying, cosmic rays streaming in all directions, magnetic fields threading through the medium in structures that span light years, the vast and patient machinery of the universe operating on timescales that make the entire history of human civilization a momentary flicker. Voyager crossed that boundary and lived to tell us about it. The telling continues, faintly, for a little while longer. And when the last signal finally fades and the spacecraft drifts on in silence, what it found will remain in the scientific literature, in the models it forced us to revise, in the questions it opened that future missions will spend decades answering, in the simple and extraordinary fact that we looked, and we listened, and we learned. The darkness is not empty. The boundary is not silent. And we know this because we had the courage to ask, and the patience to wait for the answer.